One obvious solution to detecting tampering of a ledger is to make it public. If everyone has a constantly updated copy of the ledger and somebody tries to change it, everyone else will see that right away. Come to think of it, if you have a way to keep all of the copies in sync, you don't need a central master copy of the ledger at all. All of the copies can be equally valid. If you then have a way to add blocks to the chain and have them sync over to other copies, you don't need an intermediary, a go-between, to handle the transaction. So for example, you could send money to someone without using PayPal or Venmo or Western Union or any other service. That is in fact one of the great advantages of cryptocurrencies. They can be used to improve the reliability and safety of financial transactions in countries with unstable banking systems or where it is dangerous to carry cash. That's right. Cryptocurrencies are built on top of distributed public blockchains, a blockchain where everybody can have their own copy of the entire ledger. To accomplish this, a distributed public blockchain has to do a number of things. It has to have a mechanism to keep the ledgers in sync with each other, to make it possible for anyone to determine the latest valid blockchain. It has to have a mechanism to validate new blocks, a way that anyone who gets a copy of the ledger can quickly see if a new block is valid or not, and to ensure consensus and consistency among all of the copies of the blockchain. And of course, it has to have a way to detect tampering. I'm not going to go into detail as to how cryptocurrencies accomplish this. There are other courses here on Pluralsight that teach this subject. I'm particularly fond of Blockchain Principles and Practices by Stephen Hauntz. But I will mention that one of the most common ways this is accomplished is through a technique called proof of work. Here's how it works. You saw earlier that a block hash combines the transaction data with the hash of the previous block. To implement proof of work, you also include a numeric value called the nonce. You also add a rule that the hash of a valid block must start with a certain number of zeros. Now remember, it's impossible to predict what the hash value will be for a given input. So the only way to get a hash value with a set number of leading zeros is to keep changing the input value, in this case by incrementing the nonce value, and checking the result. Getting a valid result is a matter of luck, but the average time will be a matter of statistics, and it can take a very large number of attempts, millions or billions, to get a valid hash value. This process of trying to find a valid hash value is called mining. Of course, the more hardware you have working on the problem, the better the chances you'll succeed. That's why cryptocurrency miners invest in expensive mining hardware or special software that runs on video cards. These cards have many CPUs and are designed for massive parallel processing, the same type of operation you need to create hashes. This is also why cryptocurrency consumes so much power, and people are looking for other ways to prove the validity of a block. The amount of work needed to create a block also means that it takes a fair amount of time to create a block, typically minutes. So it's not terribly hard to keep all of the copies of the blockchain in sync. For those cases where two or more blocks are found at about the same time, there are rules to figure out which block is the true valid block. Given how hard it is to create one valid block, it should be clear that tampering with any of the older blocks is virtually impossible. You'd have to not only recalculate the hash of the block you wanted to modify, you'd have to recalculate the hash of all subsequent blocks and somehow convince the world that your copy of the blockchain was accurate and all of the others were not. That's not likely to happen. While determining the hash of a block is very slow and costly, validating the hash of a block is quick and easy, as the nonce value is stored with the block. So this approach addresses both of the immutability issues described in the previous clip. It is very hard to modify the blockchain, to recalculate the hash values after tampering, and it is very easy to detect tampering, as everybody has a copy of the ledger. Comparing two blockchains is easy because, as you saw earlier, if the hash value of a block in one chain matches the hash value of the same block in another chain, you can be sure that the entire chain up to those blocks is identical.